Organometallic reagents. Carbon bonded to what? So this video, we're essentially just going over the basics of what an organometallic reagent is. It's a new type of reagent we haven't talked about before. And based on the name, what should we put in this blank? Organometallic reagent. Carbon bonded to a metal. Yeah. Which, this might be a good time just to pull out your periodic table. Where are the metals? Where are the non-metals? So essentially there's that line on the periodic table that goes like this, and all the metals are over here, and then all of the atoms we're used to thinking about, carbon, oxygen, all that stuff is over here. So now we're going to work on some reagents that the metals, the stuff on the left, is bonded to the stuff on the right. And based on what we know so far, would you say that that's going to be, and here's one organometallic reagent down here. I've just drawn it as so, but would you expect that that carbon-metal bond would be ionic or covalent based on what we've talked about so far? So you pause, you're thinking about it. Best way to learn, the best way for your mind to remember things is to do your best, give it your first thought, and then correct that thinking based on new information. And I think that a lot of you probably said ionic. That's kind of what we would have thought based on last semester's information. But it turns out that these organometallic reagents have properties that make them ionic seeming, and they have properties that make them covalent seeming. So something like CH3 lithium is often drawn like that with a real covalent bond between the two of them, but it's also often drawn as CH3 with a lone pair. And again, why is the lone pair on the carbon and not the lithium? Well, the carbon is a lot more electronegative. It's going to be pulling those electrons toward it. So even if it's drawn in a bond like that, we can recognize that it's highly polarized to that carbon, the partial negative being there, and we'd have the lithium here. So essentially the answer is it's not ionic, it's not covalent, it's got parts of both in it. So would you expect this to be a stable or a reactive species? So again, take a minute, think about that. Circle one, mark it somehow. All right, you're back with me. Well, hopefully you're kind of relating this back to acid-base chemistry. And one thing that we know about is that those electronegative elements, chlorine, fluorine, those are the ones that are really comfortable with a negative charge. And since we said this has a lot of ionic character, there's a negative charge on the carbon, we would expect that that's not going to be very happy. Carbon doesn't usually want to have a full negative charge on it. So that's going to be a reactive species, a very reactive species. We can compare it to acid-base chemistry. And the more we're going to learn about a few different organometallic reagents, the more polarized the carbon-metal bond, the more reactive the species is. The more reactive. And that makes sense. That's kind of what we already talked about with lithium aluminum hydride versus sodium borohydride. Lithium aluminum hydride is more reactive because the aluminum hydride bond is more polarized. So all this being said, what pKa value best approximates this molecule's stability? Think about that again, draw something, write something down, then unpause. All right, you've unpaused. Well, if we're thinking about this like CH3 minus with lithium plus, we would expect that would be the conjugate base of the protonated species, and the protonated species would be CH4. We know the pKa of CH4 is what? Yes, 50. It is the least acidic thing on our pKa table. If that's the least acidic thing, that means that this is the least stable. It's the most reactive. This would be the most reactive conjugate base related to our acids on that pKa table. So this is going to be a really, really reactive molecule. Yeah, all right.